Okay, so we had left off talking about locating domain restrictions for rational expressions, and then stating the domain in set builder notation. So now we're going to simplify rational expressions, but we're also going to keep identifying the domain of the rational expressions. So remember that when simplifying fractions, we're looking for common factors that can cancel. So like if we're simplifying 12 over 60, we know that 1 times 12 is 12 and 5 times 12 is 60, right? So the greatest common factor of 12 and 60 is 12. And then 12 divided by 12 is 1. So 12 divided by 60 ends up simplifying to be 1/5. So similarly, when working with rational expressions, we're going to be looking for common factors in the numerator and denominator that can cancel, that will simplify to be 1. For example, x plus 4 over x minus 3 times x plus 4. The x plus 4s can cancel, and that leaves us with 1 over x minus 3. But we cannot forget domain restrictions. So the resulting rational expression is only equivalent if it shares the same domain as the original expression. So like looking at the simplified version of the rational expression that we started with, we wouldn't see that x can't be equal to -4. So basically, we're going to be stating the domain or looking for the domain restrictions before we simplify so that we don't miss any of those domain restrictions. Okay, so for this rational expression, let's first look at domain restrictions. So we're going to set the denominator, 15x cubed, equal to 0. And we can actually, 15x cubed cannot be equal to 0. And we can actually solve this by inspection and see that x cannot be equal to 0. We could divide by 15 as well. But for now, we're just going to solve this one by inspection. So we can see that the domain here in set builder notation will be x is an element of the real numbers such that x cannot be equal to 0. So basically, the domain of this rational expression is all real numbers except for x equal to 0. Okay, so for simplifying, I'm going to break this down. We could do this, you could probably look at this eventually and do this in one step. But I'm going to first look at identifying the greatest common factor of the coefficients in the coefficient in the numerator and the coefficient in the denominator. So the GCF of 25 and 15 is 5. And I can write 25 as 5 times 5. And I can write 15 as 5 times 3. Okay. And then thinking back to when we studied exponents, and we were simplifying expressions using exponent properties, remember that x squared is x times x, and x cubed is x times x times x. So now looking to simplify here, 5 over 5 will cancel. X divided by x is 1. X divided by x is 1. So now if we look at what we're left with, we will just have 5 over 3x. Now, you do not need to write out x squared is x times x or x cubed is x times x times x. If you remember when we were studying exponents, I would say that, okay, well, there's an x squared here that will cancel with an x squared here, leaving us with just an x in the denominator. Okay, so this is the simplified version of the rational expression, and the simplified expression here actually has the same domain restrictions as the original expression, but that's not always the case. All right, so let's look at the next one. Okay, so let's think domain restrictions first. So 2x plus 1 times x minus 5 cannot be equal to 0. So thinking zero product property, this means that 2x plus 1 cannot be equal to 0, or x minus 5 cannot be equal to 0. So x cannot be equal to negative 1/2, and x cannot be equal to 5. So our domain in set builder notation is x is an element of the real numbers such that x cannot be equal to negative 1/2 and x cannot be equal to positive 5. Okay, so now we want to simplify. And the numerator and the denominator here are already in factored form, or they're written as products of linear factors. So we can now see that, okay, we have an x minus 5 here that's going to cancel with an x minus 5 in the numerator that will cancel with an x minus 5 in the denominator, leaving us with 3x over 2x plus 1. So here's the simplified version of that rational expression. We have no common factors in the numerator or denominator. Okay, and then here's also an example where if we took the domain restriction, if we looked for the domain restrictions in the simplified expression, we would have missed that x cannot be equal to 5. Okay, so domain, looking for the domain restrictions, we know that x squared plus x minus 2 cannot be equal to 0. That's going to factor to x plus 2, x minus 1. So x plus 2 cannot be equal to 0. X minus 1 cannot be equal to 0. So x cannot be equal to negative 2. X cannot be equal to 1. Okay, so x is an element of the real numbers such that x cannot be equal to negative 2 and x cannot be equal to 1. Okay, so I've already done the work for factoring the denominator. We're going to be factoring the numerator and the denominator to see what cancels. So I've already factored the denominator now and can see that the denominator will be x plus 2 times x minus 1. The numerator, I don't need to factor with guess and check. It's a linear factor, but there is a GCF there. So the GCF of the numerator is 3. So I'm going to factor out a 3 just to see if there's anything that can cancel. I want to factor as much as possible. And now we can see that the x plus 2's will cancel. So we are left with 3 over x minus 1. Okay, so domain restrictions first. X squared minus 7x plus 12 cannot be equal to 0. Okay, so x minus 4 times x minus 3 is what that factors to. So x minus 4 is not equal to 0, or x minus 3 is not equal to 0. So x cannot equal 4, x cannot equal to 3. Okay, and then here is our domain of this rational expression stated in set builder notation. Okay, so we can see that the denominator, what the denominator factors to already. So x minus 3, x minus 4. Okay, and then we need to factor the numerator, and we're hoping that we end up with one of the factors being the same as what's in the denominator. So that will be what, x minus 3x plus 10. Yes. So the x minus 3 in the numerator will cancel with the x minus 3 in the denominator, leaving us with x plus 10 over x minus 4. Okay, just kind of a reminder of the common mistakes for canceling. You cannot cancel across sums or differences. You can only cancel factors of a product from the numerator and denominator. Okay, so we know that 5x squared minus 20x cannot be equal to 0. Here we have a binomial to factor, so I'm just going to factor out the greatest common factor of 5x. So 5x cannot be equal to 0, which means x cannot be equal to 0, or x minus 4 cannot be equal to 0, so x cannot be equal to positive 4. And here is the domain in set builder notation. Okay, so we know what the denominator factors to. The numerator is a difference of 2 squares, so I know that factors to x minus 4 times x plus 4. If you didn't recognize that, you can always think about that x squared minus 16 as x squared plus 0x minus 16, and then use your guess and check. Organize guess and check. Okay, so the x minus 4's cancel, and we are left with x plus 4 over 5x. Oops. Now, we have talked about recognizing opposite binomials before when we were factoring with using by grouping, when we were factoring by grouping. So basically, if we have b minus a over a minus b, and you recognize that, that simplifies to being -1. And the reason that is, so if I have b minus a over a minus b, it looks similar, but the numerator does not match the denominator. But if I were to factor a -1 out of the numerator, that would make the numerator negative b plus a, which by the commutative property of addition, I could switch those two terms to have that written as a minus b. And now we can see that the a minus b's would cancel to leave us with -1. So recognizing that, that can save you a step, but also just help you with simplifying. So even if you write out the step of factoring out the -1. Okay, so first let's look at domain restrictions here. So we know the denominator cannot be equal to 0. So that factors to x plus 5 times x minus 2. So x plus 5 cannot be equal to 0, or x minus 2 cannot be equal to 0. So x cannot be equal to -5, or x cannot be equal to 2. Okay, and then to simplify, we have the denominator factored already. And the numerator is a difference of 2 squares, so that factors 2 minus x times 2 plus x. Now, looking for factors to cancel, the 2 minus x looks similar to the x minus 2, but not quite. Wrong. They're opposite. The terms have opposite signs. So I'm going to factor a -1 out of the 2 minus x. And when I do that, I'll be left with x minus 2, right? It switches the signs of each of those terms. So now I can see that x minus 2 in the numerator will cancel with x minus 2 in the denominator. I'm going to pull the negative out front instead of leaving it in the numerator, so that I have 2 plus x over x plus 5. Okay, so 25 minus x squared cannot be equal to 0. Difference of 2 squares again. So here we would have negative x cannot be equal to -5, and dividing by -1, x cannot be equal to +5. And x cannot be equal to -5. Okay. So for simplifying, we've done the work in the denominator already. And the numerator has to be 2x and an x. And here it might be helpful to do our organized guess and check. So I'm thinking 5 and 3. So how about -5 there and a +3? Yeah, because that would be -10x plus 3x is -7x. So 2x plus 3 times x minus 5. So the x minus 5 looks close to 5 minus x, but they're opposite signs. So in the denominator, I'm going to factor out a -1 from the 5 minus x. So this time I'm leaving the numerator alone. I could have factored out a -1 from the x minus 5 too to make it match the 5 minus x, but I'm going to change this so that it's x minus 5. So now I can see that the x minus 5s will cancel. Again, I'm going to pull the -1 out front. I don't have to write a -1. I can just put the negative to mean -1. Okay. So that was simplifying rational expressions, and we're going to still be simplifying in the same way, except for we're going to be looking at rational functions. So just like we started we started factoring with quadratic expressions, right? We started factoring before then we studied quadratic functions. And you could then represent quadratic functions in factored form, or we completed the square with quadratic expressions first, and then we used completing the square to rewrite a quadratic function in vertex form. So now we've looked at rational expressions and how to simplify rational expressions, and we're going to use that skill to help us simplify rational functions. And rational functions, we can we have an input and an output. that we can then represent those rational functions graphically. So here, this is in rational functions have the form r of x equals to p of x over q of x. So that's using function notation. So p of x and q of x are polynomials where q of x cannot be equal to 0. But r of x is really just the output value for the function. So I can always represent r of x with a y as well. So y equals to p of x over q of x. Same thing. And the domain of a rational function consists of all real numbers x such that the denominator q of x cannot be equal to 0. So same as for rational expressions, we're going to find the domain in the same way. And I have the order here written. I have a couple typos here. So I'm going to actually find the domain first. That's going to be our first step. And then simplify. And then we will evaluate the function at x equals to -2. Okay, so let's look at domain restrictions first. 6x squared plus 18x, the denominator cannot be equal to 0. I'm going to factor out the GCF of 6x. Oops. Okay, so we can see that 6x cannot be equal to 0, so x cannot be equal to 0, or x plus 3 cannot be equal to 0. X cannot be equal to -3. So x is an element of the real numbers such that x cannot be 0 or -3. Okay, so we have our domain, and now we want to simplify. So I'm just rewriting the function f of x in a simpler form. And in future classes, like Algebra 2 or Pre-Calculus, whenever you revisit rational functions again, you're going to want to simplify in order to identify characteristics about the graph of the rational function, but also to have a better idea. So the graph will look very similar to the simplified version of the function, but there may be something, because of domain restrictions, something we refer to as like a hole in the graph, or versus like something we refer to as vertical asymptote. So that'll be useful. For now, we're just going to simplify and we're going to evaluate the rational functions. We're finding the domain, but in the future, you guys will be graphing these types of functions. Okay, so we already know the denominator factors to 6x times x plus 3. The numerator should also factor to 2x minus 1, x plus 3. So we can see that the x plus 3's cancel. And we are left with 2x minus 1 over 6x. Now in class I showed them that the graph, like if you type in the original function here into your calculator to graph, and you were to type in the 2x minus 1 over 6x, the graphs would look like they just overlap. They're the same graph. However, typing in the original rational expression, you would actually be able to see, well, maybe not see on your calculator, but if you were to look at the table of values, or use the trace feature on your graphing calculator to see like what the y value is at x equals to 0 or x equals to -3, you would see that y is undefined. It would give you no y value back. Versus if you were to substitute a value in that is in the domain, like x equals to 2, you would get the y value, or x equals to -2, you would get the y value that goes with x equals to -2. Okay, so now for evaluating the rational expression, the rational function at x equals to -2, because -2 we can see is in the domain of this rational function, we can actually substitute -2 into the simplified version of the rational function. So that'll be -5 over -12, which the negatives will cancel, and that's just 5/12. But if we were to substitute -2 up here in the original function, we would also get 5/12. Okay, so let me adjust. I have a couple typos here again. So let's do domain first, then simplify, and then here's another typo. This should be capital G of 4, since the name of this function is capital G. Okay, so simplifying, we can actually probably just see by inspection that x cannot be equal to +7. But x minus 7 cannot be equal to 0, so x cannot be equal to +7 if we want to write out all of our work. So x is a real number such that x cannot be equal to 7. Okay, so there's our domain. So that means that when we try and evaluate g at x equals to 4, we know 4 is in the domain. Therefore, we'll be able to substitute 4 into either the original function or the simplified version of the function. So for simplifying, we didn't have to do any factoring for the denominator. The numerator is a difference of 2 squares, so factors to x minus 7 times x plus 7. So the x minus 7s will cancel to give us just x plus 7. And you guys know that the graph of x plus 7 is just a line with a slope of -1 and, a slope of +1 and a y-intercept of 7. So the graph of x squared minus 49 over x minus 7 actually looks like a line. Looks like x plus 7, but there's what we call a hole at x equals to 7. So basically you can input like 6.99, 6.9999, and so on, like all the way up to x equals, like, except for x equals to 7. So you can evaluate the function for 6.99999 or 7.0000001, and so on, just not x equals to 7. We say that there is a hole at x equals to 7. And in class we compared the graphs, and we did this on our graphing calculator. Oop, laundry's done. Okay, so for evaluating the function at x equals to 4, because 4 we can see is in the domain of g, we can just substitute 4 into the simplified version of the function, and we get 11. So at x equals to 4, y is equal to 11. Okie dokie, so we will talk about this more in class next time.